Assalamu alaikum, doctor.
Wa alaikum assalam. Do you hear me well?
Yes.
Excellent. And then let me start sharing. Okay, assalamu alaikum. Since you have just finished a lecture, I expect that those who are joining the lecture have already joined. So let us start because we only have 40 minutes. The first half of this session is going to be about the spinal cord. And as you already know, the spinal cord is the second half of the central nervous system. We introduced the first half, which is the brain. And there are a few things which are in common. I just want to, let me see what is in the chat. Yes, attendance, just attendance. Okay. We want to discuss the things that are common in the first few minutes. Yesterday, we started classifying white matter and gray matter, and we said gray matter elements include ganglia outside the central nervous system, but they include nuclei, and they include centers, they include entities. These are the gray and the cortex, of course, of the cerebrum and the cerebellum. And we also shed some little light about white matter components. And these include tracks and pathways. And now we might go into a more terminology used as in the with regards to the gray matter and white matter areas, and we will do that. I guess you already had a lecture on the spinal cord yesterday, histology lecture, so you are now probably familiar with the terminology used with regards to the spinal cord. But before we go into the spinal cord itself, we would like to speak about some common features with variations. For example, you might have noticed that the brain has its gray matter on the surface and on the inside. And this is the only place where you find gray matter of the central nervous system on the surface, which is the cerebral cortex and the cerebellar cortex. The remaining parts of the central nervous system, it's always the white matter on the surface and the gray matter on the inside. And this applies to the brain stem, and it also applies to the spinal cord. So the spinal cord, like the brain stem, has its white matter on the surface and has its gray matter on the inside. And you already, I think, saw that yesterday when you had your histology lecture. Now, let us move on, and then we will shed more light on these white and gray matter elements, just briefly, just to align that with the external features of the spinal cord. Now, Bismillah ar-Rahman ar-Rahim. With regards to the spinal cord, it's a cylindrical structure. It's a cylinder of both gray and white matters. And as I told you, the white matter is on the surface and the gray matter is on the inside. The white matter and the gray matter, because the spinal cord is cylindrical, the white matter is arranged in the form of columns of gray matter and columns of white matter. And what you see in the sections is actually the sections of the columns. So we have white matter columns and we have gray matter columns, and you probably already covered that in the histology lecture. The white matter columns are three: one ventral or anterior column, one lateral column, and one posterior or dorsal column of white matter. And they retain that name. But the section of the gray matter is used to describe the gray matter. So it is not an anterior horn and a posterior horn and a lateral horn, but rather, sorry, it's not an anterior column, posterior column, or lateral column, but rather they are named based on what you see in the section. So in the section, you see an anterior or ventral horn, and you see a posterior or dorsal horn, and you see a lateral horn. And of course, on yesterday's lecture, you were already told that the anterior horn is for motor neurons, posterior horn is for sensory neurons, and the lateral or intermediolateral horn is for autonomic elements, particularly the sympathetic neurons. So this is on the inside. So it's a cylinder of gray and white matter columns. In the upper it is found in the upper 2/3 of the vertebral canal. In the embryo, it spans all the cavity of the spinal canal. But as the individual grows, the growth of the skeletal elements of the body is faster than the growth of the neural components. And so it is not that the spinal cord is shorter, but rather the vertebral column becomes longer. And so in the adult or even in young children, it only occupies upper 2/3 of the vertebral column. Starting from, and you remember yesterday, I said in any book or site or whatever, they say it starts from the foramen magnum. Or in fact, it starts just below that because the foramen magnum is occupied by the spinal medulla. And it continues up to lumbar vertebra number 1 or probably lumbar 2. So it spans this space. Now, like the brain, the spinal cord is covered with meninges, and of course, in the spaces between the meninges, particularly the subarachnoid space, there is cerebrospinal fluid. And as you know, this CSF is for, we will talk about it a little more later on, but it is for purpose of nutrition and protection. Now, it is a processing and relay station, and these two are very important. You will hear more about this in physiology lectures, but processing, like in the brain, some sort of processing takes place at the level of the spinal cord and at the level of the brain stem, and then at the level of the cerebellum, and the higher level processing takes place in the cerebral cortex of the cerebellum. But it is also a relay station. Relay stations, sometimes some processing takes place at relay stations, and there is a very important term used in physiology to indicate function, which is modulation. Modulation means changing whatever is going on through the relay station. But not many modulation takes place at the spinal cord level, but as more of it takes place at the level of the brain stem. So we have some sort of preliminary perception and some modulation taking place in relay stations, particularly in the brain stem. But in the spinal cord, it is just a relay station for some minor processing. Now, as you can see, these are three meninges. This is the dura, meta, the top there, and at this middle part of the section, as you can see, the dura meta is reflected out, and we can see the arachnoid. The dura is thicker, arachnoid is very thin, and the pia is actually attached to the spinal cord. So the outer dura is thick, and the arachnoid is thin and web-like, and the pia is attached to the spinal cord. The subarachnoid space, this one which is open, contains cerebrospinal fluid together with the blood vessels, as you can see, and also the roots of the spinal nerves. So you can see the roots of the spinal nerves in the subarachnoid space, and they exit by piercing the arachnoid and dura. And in fact, the spinal nerves carry with them a covering from the dura and a little bit of arachnoid, but it disappears later, and then we just have the dura and pia. The dura and arachnoid are fused together to form the covering of the nerve, which is the epineurium, or the capsule of the nerve. This is another illustration. It makes it clearer. These are the coverings: dura, arachnoid, and pia. And as you can see, the nerves are found in the subarachnoid space, especially the nerve roots. And by the way, these are rootlets, a posterior root and an anterior posterior root there, and an anterior root here, formed of rootlets. And then these rootlets form a thicker part that makes the nerve trunk. And on the dorsal root of the nerve, this is the rootlets and this is the root. And in the dorsal root, there is an enlargement, which is the dorsal root ganglion. And then we have the nerve trunk. Now, this is the trunk there, starting from here, and this is the nerve trunk. The rootlets and part of the roots are found in the subarachnoid space before they pierce the arachnoid and take a covering with it in the covering to the nerve. This is a soft tissue specimen, and as you can see also, it's open. This is the dura, and this is the arachnoid. And the PA, of course, is covering the spinal cord itself. These are the nerve rootlets. You see them in the subarachnoid space. And by the way, we will mention that, but it is very beautiful in this illustration or actually photo. Some of the part of the arachnoid actually holds the spinal cord through what is known as the denticulate ligament or ligamentum denticulatum. Ligamentum denticulatum, it's like a tooth. And this is part of the arachnoid, and this is the ligamentum denticulatum. This is a larger view, and as you can see, this is the denticulate ligament holding the cord to the bone, ligamentum denticulatum. These are the rootlets of the nerve roots, and this is the spinal cord. Now, here you can see the blood vessels, very clear. This is anterior spinal artery in the subarachnoid space, and of course, this is the spinal dura meta, and then the dorsal root ganglion there. Now, the spinal cord is segmented. It has got 31 segments, and we discussed that earlier. We have 8 cervical in a state of 7 because we have 7 vertebrae. So we have one more. It's not one. It's one more segment. So we have 8 segments. And when we go to the end of the spinal cord, we only have 1 coccygeal nerve, while we have 4 coccygeal vertebrae in the coccyx. But so we have 3 less at the lower end and one more at the upper end. So 33 becomes 31 segments. A segment is actually a part of the spinal cord that gives rise to a pair of nerves. So it's a segment with neurons, and these neurons forms one nerve or a pair of nerves. So we have 31 segments giving rise to 31 spinal nerves. So a pair of spinal nerves is attached to each segment. Now we have 8 cervical, as I mentioned earlier, we have 8. Because we have 8, the first cervical actually emerges above the first cervical vertebra, which is the atlas. And then we have one between the first and second, and then we have one below the seventh. So we have one above the first and one below the seventh. So we have 8 cervical spinal nerves. Now, then below each of the 12 thoracic vertebrae, we have a thoracic nerve, and then we have 5 lumbar, 5 sacrals, and one coccygeal. This is just an enlargement to use it first as a reminder. This is the dura, arachnoid, and then the pia. These are the rootlets inside the subarachnoid canal, and these are the spinal nerves with dorsal root ganglia outside the meninges. This is a soft tissue specimen showing the same. Let us move on. This is also a soft tissue specimen showing you the nerves, but this one I brought it to show you one very important issue. As you can see, because the spinal cord is shorter than the vertebral column, nerves have to come down a little bit to exit through the intervertebral foramen. So this is the intervertebral foramen, and as you can see, the nerve goes down a little bit and obliquely, then it exits through the intervertebral foramen. This is very important, and you need to know that the segment is not against the intervertebral foramen. The nerve emerges from the intervertebral foramen, but the segment is higher than the nerve. And as you go down, this obliquity increases because there is a larger difference in the spinal cord and vertebral column. Now, when you look at the spinal cord itself, it is enlarged in 2 places. It is enlarged in the cervical part of the spinal cord, and this is called the cervical enlargement. And then we have a lumbar one in the lumbar region. And why is that? Because the white matter and gray matter elements in that part of the spinal cord control the nerves, the muscles and skin and skeletal elements of the upper limb, the cervical region. And then in the lumbar region, they control the skin and the muscles of the lower limb. So we have more nerve cells there. This is why the spinal cord is enlarged, because of the upper and lower limbs, due to cells and fibers of the limbs. So the spinal cord itself ends inferiorly in an enlargement, and there we have the enlargement because from that enlargement we have many nerves emerging, all the sacral nerves and the coccygeal nerve. And this enlarged pointed part is called the conus medullaris, the conus medullaris of the spinal cord. And this is conus medullaris is anchored to the coccyx by a meningeal extension, mainly pia, with a little bit of arachnoid, and it is called the filum terminale or the filum terminale. Filum terminale or the filum terminale. This anchors the conus medullaris, the lowermost end of the spinal cord, to the coccyx. And then, of course, you already saw the spinal cord is held to the vertebrae by ligamenta denticulata. The singular is ligamentum denticulatum. There we have, this is the lower end of the spinal cord, and as you can see, this is the lumbosacral enlargement, and this is the cervical enlargement at the upper end. And then we have the tapering end, which is the conus medullaris there. And then we have extension of the pia and arachnoid to anchor it, and which is the phylum terminale. Now, because many nerves come from the lowermost end of the spinal cord, and they come together and they come down to exit through intervertebral foramina, they form a bundle of nerves known as the coda equina. Coda equina. So if we have another there, this is, as you can see, the nerves come down steeply, obliquely, and this is the lowest most end. This is the conus medullaris, and this is the phylum terminale. You can see it very clearly there. This is the conus medullaris, and this is the phylum terminale, and this is the coda equina. Coda equina is the collection of nerves, lumbar and sacral nerves. This is an illustration. This is the lumbar enlargement up there, and we will describe a little bit these fissures in a little while. This is the arachnoid, and here the arachnoid is removed. This is the dura, and here the dura is removed. These are the nerve rootlets inside the subarachnoid space. And this is the conus medullaris, coda equina, and phylum terminale, the phylum terminale holding it to the coccyx. Now, the surface, like the medulla, is marked by furrows or grooves. And these grooves are a deep ventral anterior median fissure. It is anterior and median. Sometimes they just call it the ventral median fissure. Sometimes they just call it the anterior median fissure. And sometimes they call it the median fissure because it is by definition found on the anterior surface, and it is the anterior or ventral median fissure. Then we have a dorsal one in the posterior side, and it's also called the posterior median sulcus because it is not as deep as the anterior one, so it is it's a sulcus rather than a fissure. And then we have two dorsolateral and two ventrolateral. So we have one posterior, one anterior, two on each side. One of them is dorsolateral and one is ventrolateral. Now we have a dorsal intermediate sulcus. So we have another intermediate sulcus between the dorsolateral and the posterior median fissure. And of course, you saw that why do we have these fissures? Because of the columns. Because of the column. Posteriorly, we have a dorsal column, but it has got two bundles. Now, if we the first thing you need to know, you already saw it in histology, is that the anterior median fissure is deep, so it's a fissure, while the dorsal one or the posterior one is just a sulcus. And then we have one there for the emergence of the posterior root of the spinal nerve in the form of rootlets. And this is the posterior dorsal, the posterior, the dorsolateral fissure. And then intermediate fissure there between the two. Why we have intermediate fissure? Because we have a posterior funiculus or column, and it is subdivided into fasciculi. Funiculus is a column, fasciculus is a bundle. So the dorsal column or funiculus is further subdivided into fasciculi, the cuneate and the gracile, the cuneate fasciculus and the gracile fasciculus. So this is why on the surface we have another additional fissure or sulcus, sorry, sulcus. While anterolaterally, we just have the ventrolateral or the anterolateral sulcus. This is the point of exit of the ventral rootlets of the ventral root of the spinal nerve. There you can see them very clearly. The posterior surface has got two. These are actually the gracile. They call it on the outer side, the gracile tubercle, this one. And then we have a cuneate tubercle. And we have the dorsal central fissure, dorsal central or median fissure, dorsal median fissure. And we have the intermediolateral there, and intermediate or posterior intermediate sulcus between the two tubercles. The tubercles are a reflection of the fasciculi, the two fasciculi, cuneate and gracile fasciculi. This is a soft tissue, another soft tissue section showing the same. This is what I wanted to say about the spinal cord. I will give you a chance to ask questions before we proceed to the second half of this session, which is, we don't need more than that for it. We can cover what I want to talk about as far as the early development of the nervous system. Any questions? Spinal cord?
No, doctor, it's clear.
Yeah, topography of the spinal cord. The second half is the early development of the nervous system. Very simple and straightforward, doesn't really need a lecture. As we sometimes do, always do, Bismillah ar-Rahman ar-Rahim, then we give a reminder. And I want you to give me the reminder. You know about this. Of course, there's fertilization, formation of the zygote, then mitosis. Cells divide and divide and divide. They make a hollow ball called, yes?
Are you sharing?
Yes. Sorry. There, share, and then let us go back, starting from there. Okay, the early development of the nervous system. Now we wanted to start with a reminder, as we always try to link between what we already know and what we are going to discuss. So in early development, generally speaking, the early development of the embryo, starting from fertilization, giving us a zygote, then division, mitosis, leading to the formation of a blastula, which is a hollow ball of cells. A hollow ball of cells, this is a blastula. And then an invagination takes place on this blastula, making the gastrula. And the gastrula will have cells arranged on the surface, and they call it the ectoderm. Assalamu alaikum. I'm fine. I'm having a lecture. Can you call me, say, in 10 minutes? Okay, 10 minutes. Sorry for the interruption. So when we end up with a gastrula, in the gastrula we have a layer of cells on the outer surface of the gastrula, and this is called the ectoderm. And then the lining of the invagination forms another layer, which is the endoderm, and between the two is another layer of cells called the mesoderm. You already know this. So our discussion of the development of the nervous system starts from the gastrula, And here you can see the gastrula with ectoderm, ectoderm in this plate in the middle, and then this one, endoderm, and in the middle we have the mesoderm. You know about the notochord. Now, next to the notochord, the nervous system starts its development. So the development of the nervous system starts in the third week, mid-third week, day 17, day 18, the process of formation of the nervous system starts. This is just fertilization, zygote, blastocyst, and then the gastrula, blastula, and then gastrula. And this is ectoderm, mesoderm, and endoderm. This is how it looks in side vision, side look. It looks like that. This is amniotic cavity with fluid, and then we have the ectoderm facing the amniotic fluid on this side, the mesoderm in between, and the endoderm of the yolk sac. From the ectoderm, what we have the epidermis, the skin, and all the epidermal derivatives, including the hair, nerves, sweat glands, mammary glands, etc. Then we have the nervous tissue and sense organs. We have the nervous tissue and sense organs from the ectoderm, in addition to elements of the endocrine system related to the nervous system, the pituitary gland, the adrenal medulla, and enamel of teeth and the lens of the eye. This is what we are concerned with, the ectoderm. This is about the mesoderm and endoderm. We don't need to worry about that today. So this reminder, this is how it looks like in the section, and this is just further description of each component. I put it there just for you as a refresher. When you go through the PowerPoint again, it just reminds you about what develops from which part of the blastula. Now, after the blastula, something happens called neurulation. Then the formation of a neural tube, neurulation. And it starts with the formation of a thickening in the ectoderm. And it happens, as I mentioned earlier, in the mid part of the second week, about the day 17, day 18. What happens, there is thickening of the cells of the ectoderm in the center next to the notochord. And this thickened plate is called the neural plate, So the neural plate forms at that time. Then a groove takes place on the neural plate. The groove is formed because the side of the central part of the neural plates become elevated a little bit, making a fold. So it folds, and when they fold up, we have a groove appearing between them, and this groove is called the neural groove. So we have two folds and a groove in the middle. At the junction, at the height of the neural folds, we have special cells called the neural crest cells at the junctions of the fold. You can see them here in green. Okay. The bluish one is the remaining part of the ectoderm. We have then at the junction of the fold, the neural crest. And this neural crest contains the neural crest cells. And this is the actual neural plate starting to form the neural tube. Then they fuse, the folds fuse there to form a neural tube. And then the neural crest cells separate as neural crest cells, and the ectoderm, the remaining ectoderm, forms the epidermis of the skin on the surface. And then we have a neural tube. Now, these neural crest cells form the components of the peripheral nervous system, including spinal ganglia, including autonomic and peripheral nerves and autonomic nervous system and everything. All of that form the peripheral nervous system from the neural crest cells. This is an external view showing you the starting from 18 day, day 18 of development, the appearance of the neural groove and the neural groove and the neural folds there. And then they started fusing to form the tube. And by the way, during development, the anterior end and posterior end remain open for some time, and they call them the anterior neuropore and the posterior neuropore. And then, of course, development, the somites developed to form the bone and muscle around the spinal cord. And there we have the closed neural tube, the 23rd day of gestation. So just the first few days in the 4th week of development. Now, then the cranial end of this neural tube enlarges a little bit to form 3 vesicles. These 3 vesicles are known as the prosencephalon, the mesencephalon, and the rhombencephalon. The prosencephalon will give rise to what is known as the forebrain, and the mesencephalon will give rise to the midbrain, while the rhombencephalon will give rise to the hindbrain. So we have 3 vesicles to start with. These are the 3 vesicles, and this is a side view. This is a side view. We have the prosencephalon leading to the forebrain, mesencephalon, the midbrain, and rhombencephalon, the hindbrain. And this is a side view for the same issue. And this, as I told you, between week 3 and week 4 of the embryonic life. Then what happens in the 4th week and the 5th week? We have some these by the way, these are known as primary brain vesicles, primary. Then some secondary brain vesicles appear. So the prosencephalon will give rise to side dilatations. One of them is it divides into 2 dilatations. One of them is the telencephalon, while the other one is the diencephalon. And also the rhombencephalon will also subdivide into 2 vesicles, the metencephalon and the myelencephalon. Now, of course, you now know the telencephalon will give rise to the cerebrum. Diencephalon will give rise to the diencephalon, thalamus, hypothalamus, metathalamus, epithalamus, and the rest. The mesencephalon will form the midbrain, while the metencephalon will give rise to the pons, and the myelencephalon will give rise to the spinal cord. So after it bends forward more, the prosencephalon forms 2 vesicles, the telencephalon, which give rise to the cerebrum, and the diencephalon, giving us the thalamus, hypothalamus, etc. Then the rhombencephalon forms 2 vesicles, the metencephalon giving the pons, and the myelencephalon giving us the medulla oblongata. So there is the summary: prosencephalon, forebrain, but divided into 2, telencephalon and diencephalon. The telencephalon cerebrum, diencephalon actually the diencephalon. Then we have the mesencephalon giving us the midbrain. The rhombencephalon will give us the metencephalon and myelencephalon, which are the pons and medulla. Then we have, of course, the spinal cord. This is just a side view of the same concept, and this is a 3-dimensional image showing you the same issue, and with additional parts, which are the optic vesicle. It's an additional one that makes the eyeball. And this is a summary of the whole thing. We have the telencephalon, diencephalon, mesencephalon, and rhombencephalon giving us the different parts of the nervous system. When you Google congenital anomalies or malformation, what you are going to get are actually congenital anomalies of the structural elements surrounding the nervous system and not the nervous system itself. We have abnormalities of the development of the cranium, like the anencephaly, like cranioraxesis and the open spina bifida, the closed spina bifida, anencephaly, encephalocele, and the closed spina bifida. So all of these are actually abnormalities related to the central nervous system and not abnormalities of the nervous system. Thank you very much. This is what I wanted to introduce, which is the early development of the nervous system. Any questions? Okay, we will have the usual break. We meet again at 5 past 9. Okay. You use the same link after 15 minutes.